My name is Soukaina Firmli, and I'm a PhD student in Mohammadia School of Engineers. This work is in collaboration with Oracle Labs, and it's called CSR++, a fast, scalable, update-friendly graph data structure. So this work has been published as a conference paper and accepted in the 24th International Conference on Principles of Distributed Systems, and it's mainly centered on designing and implementing an efficient data structure for to store graphs and to enable mutations, meaning updates on graphs. Okay, so to start with, I'm gonna give a bit of context on graph analytics and systems. So initially, the graph models, the graphs allow to model real-world data as a relationship between entities called vertices, for example, Ali, Mark, and Jane in this example, and relationships between them called edges to gain new insights that are not seen when using classic other models such as relational models. So the graphs systems are actually aimed to process real large graph data, and they rely on efficient data structures to support the fast, for example, fast read-only workloads, meaning analytic workloads such as algorithms, PageRank, weakly connected components, and other algorithms. They also rely on efficient data structures to allow fast mutability, meaning that we need to be able to update graphs in a tiny manner, in a fast way, but also they need to allow for low memory consumption, low memory footprint, since we're talking about large-scale big data graphs that can hold billions of edges and need to be stored efficiently in the memory. So graphs actually, as a proof that graphs are becoming very important in today's technology trends. We see that Gartner's ranked graphs as number 5 trend in their top 10 data and analytics technology trends for 2019. So to give more details about the work that we've been carrying on, I'm going to talk about graph data structures and then mutations. So graph representations aim to store vertices and edges in a efficient way. Some of the classic example of those data structures, we find the HACC list and then CSR, but the main gain from implementing a graph in HACC list is the high update, the high immutability performance. CSR, on the other hand, is a compact way to store graphs. It's the fastest read-only data structures there is. It has really high performance, high analytic performance, since we only store indexed arrays, compact arrays of vertices and edges. It has really low memory. So when we're talking about graph updates, we're talking about insertions and then deletion of vertex and edges for vertices and edges. There are multiple techniques, but the main ones are actually listed here. So we have the in-place updates, meaning that we don't have to perform copies of the whole graphs. We have, so for example, the Boost Graph library that we're going to evaluate later. We're going to show some evaluation numbers on that. Batching, meaning that we actually collect a number of updates, collect a number of edge insertion, for example, into batches, and then perform them at once to allow for optimal update operations. And then we have this technique called snapshotting or creating deltas that is mainly useful when we have data structures that are immutable, like CSR. Whenever we have to perform analytics and perform scans, we will have to scan both the original data structure, which is, for example, CSR, and then we'll have to scan the deltas as well. So that actually, that is the trade-off, and that lowers the analytic performance. So this naturally leads to asking the main question, which is like how to enable fast in-place updates while maintaining high analytic and low memory footprint. So the answer is that we developed is CSR++, which is a fast, scalable, update-friendly graph data structure. And we're going to talk more in details about the design ideas and solutions to answer this main question. So first of all, we're going to talk about the design, meaning the vertex and edge data structures in CSR++. We're going to talk more about the properties, since we're mainly addressing property graphs in this case. And then we're going to talk about the update protocol. And next, we're going to give some breakdown of the performance analysis of CSR++, and then we're going to conclude by a small conclusion. So initially, since we talked about the graph data structures, we gave two main examples, the adjacency list and then CSR. So the adjacency list allows for per vertex flexible edge updates, meaning that if we want to update an edge, we only have to, if we want to insert an edge, for example, we only have to access the edge array and then perform updates on it. Whereas in CSR, we'll have to copy the edge array, because the edges are stored in a compact manner, in a continuous manner. So in one side, CSR is actually very fast, since we have compact format, we have fast indexed, array indexed access. So it's more cache friendly, and it allows for better locality. But the adjacency list allows for faster updates and faster edge array handling in case of mutation. So the idea here is to combine both the array continuity of CSR, meaning that we design CSR++ as compact arrays of vertices, for example, with the flexibility of updates of adjacency lists. So to present a high-level design of CSR++, we really can give the details on how we store the vertices and then how we store the edges. So the vertices are stored in segments, meaning the graph is actually a list of segments. Each segment stores a fixed number of vertices, and then this way we have a cache-friendly way to traverse these vertices. And then we have this optimization, which is low degree aligning, meaning that unlike the adjacency list, where every vertex has to have a pointer to its neighbors list, in this case, in CSR++, we have this optimization where in case we have a single neighbor in vertex, we actually embed that edge in the vertex array. That way, we can actually store the actual edge instead of the pointer. That allows for memory optimization. And the edges themselves are actually arrays that are expandable arrays, meaning that when we want to update an array of edges, in case we want to insert a new edge, when we don't have space, we can actually grow that array. We can allocate double the original size, and that allows for really fast in-place updates. And then for really fast in-place updates, and then in a multi-threaded context, we mentioned that CSR++ is actually a concurrent data structure. So in case we have multiple writes, we allow for, we have a synchronization mechanism that's based on locks. Those locks actually protect each segment from concurrent writes and allows for synchronized updates. So it is worth mentioning that we keep the edges sorted, meaning like we keep the semi-sort property of the graph for better cache usage. It actually gives really better performance when we're applying analytic read-only. So basically, we talked about how CSR++ kind of like combines ideas from agencies list and then CSR to allow for fast analytics, but as well as fast in-place updates. And then we're talking about, when we're talking about CSR, talking about compact ways to store entities. So here we have, in CSR++, we have compact vertex arrays, as well as compact edge arrays when we're loading the graph, meaning that we have a smart loading by implementing a smart allocation protocol that could allow us to allocate the edges initially in a contiguous manner. So here we're going to talk about details on how segments are implemented, are designed. So basically the graph in CSR++ is represented as chunks called segments holding a fixed number of vertices. So here we have an example of a segment. Each segment actually has a lock, and then that lock enables for synchronized writes. So the segment is basically compounded of a lock, a list of vertices, which is here, like we have 4 vertices, for example, and then we have a vector of pointers to vertex properties. We're going to talk about vertex properties later, but here we're talking about topology, meaning like the vertex and the edge structures. So basically each vertex here holds 3 data. So we have the length, which stands for the degree of the vertex, the number of neighbors, and then we have a pointer to the neighbor's list. So here we have a union struct, meaning that if the length is greater than 1, then we're gonna have a pointer to the edge list. But if we have the length equal to 1, as I said before, we're gonna inline the edge, we're gonna embed it in the segment structure, and then we're gonna store it there instead of the pointer. That allows for really good memory consumption. And for the edges, how they're represented, they actually hold 3 fields. First of all, the deleted flag. We're going to talk about deletions later in the update protocol. And then the vertex ID, meaning like the index of the vertex in the segment. And then the segment ID, since we have the graph as represented as a list of segments, we need to actually locate the edge in which segment it is. So we're going to talk in this slide about how CSR++ stores properties. So we need to store basically vertex properties and then edge properties. So in this example, we have, for example, 2 segments, and then the way we store vertex properties in CSR++ is in arrays that are parallel to the segments. So as I mentioned before, each segment holds a vector of pointers, and each pointer actually points to an array for vertex properties. So for example, if we have the index of a vertex, we can deduce the index of the property value of that vertex in a given vertex property array. So this way, this actually allows for fast index accesses to the vertex properties. So for edge properties, actually we have the same segmentation approach as for edges. That is to say, we have for each edge array, we have a parallel vertex, we have a parallel edge property array, which stores the edge property values in an aligned manner. So for example, we have 2 edge properties, example here below. So all the edge property values for the 2 properties are actually stored in the same array, but we have this logical formula to access the edge property values for a given edge and for a given index. So this way actually allows for a better, fast per vertex update, meaning that if you want, for example, to update an edge, we don't have to copy the whole edge property array of the whole segment, of the whole vertices of the same segment, but we actually can only update a certain given specific edge property array in a separate way. That allows also for easy reallocation of the property arrays and then easy reordering. Next, I'm gonna talk about, so now that we talked about the design of the topology, meaning how we store vertices and how we store edges and then properties, we're gonna talk about the update protocol of CSR++. So the update actually, the updates are, can be defined as three main update protocols: the vertex insertion, the edge insertions, and then the deletions for both vertices and edges. So for vertex insertions, we're going to start with this one. So this slide presents an example how the vertex insertion is implemented. So to be able to insert a new vertex, we always check for the last segment. So usually, you know, after we populate the segments, we have either some space left in the last segment or we don't. So in case we have, we're gonna actually make this vertex valid, meaning that we're gonna, so initially the length and the degree of the vertex is actually -1. So that's how we know that the vertex is valid. So we're gonna check for the last segment and see if we have enough space, and then if we do, we're gonna find the first first invalid vertex, and then make it valid by incrementing the degree of that vertex. So the other case is if the last segment is full, actually allocate a new segment and then allocate a new vertex property arrays along with it. And then the way we actually keep track of those newly allocated segments, that we have this indirection layer that we have here. So this indirection layer is nothing but just an array of pointers to those segments. And if we want to allocate a new segment, we only have to copy this to expand this array by doing like a copy on write. And this is usually very fast. So the only cost here, as I mentioned here, is the copy on write of the segment pointer array, what we call the indirection layer. So next is the edge insertion update protocol. So as I mentioned before, we have in CSR++, we implement growable expandable arrays, meaning that when we want to insert a new edge, if we have enough space, then if we don't have enough space in an array, we actually double the allocate new array and then double the size of the original and then perform copy on write. We use relocation method in C++, but this can be actually implemented in a smarter way, and then allowing for faster copy on write, faster relocation. So the thing here is that, for example, here we have four edges. So in order to insert a new edge, we actually double the edge array, and then we keep space, we keep extra space for new incoming edges. So basically, CSR++ is actually a concurrent data structure. So we said that we protect each segment with locks. So in our case, as we're going to mention in later in evaluation section, we actually evaluate CSR++ in a multi-threaded context, and we allow for concurrent writes into the edge and then the edge arrays. So to be able to have synchronized and to protect those write operations, we actually use lightweight spin locks, and every time a thread actually can hold a lock and then perform the updates on a certain edge array. For deletions, for the update protocol to perform deletions, so we have implemented logical deletions of vertices and edges. So for vertices, as I mentioned before, we have this length field that stands for the degree of the vertex, which is initially -1. So -1 means like valid vertex. So the optimal way to actually implement logical deletion for vertices is to use that field and then set it to actually -1 if you want to mark it as deleted. For edges, we have a separate deleted flag, and then we have to set it to 1 to mark it as deleted. So the cost of this is the fact that we'll have to add extra conditional branches in traversal when deletions become very frequent, meaning that we have a lot of X's in segment arrays, and then in edge arrays, we're allowed to perform compaction. By compaction, we mean like we're going to reuse the space that was used by the deleted vertices or edges, and then kind of like compact the arrays and then remove the unused space, basically. That compaction would mean actually like a whole copy of the segments, the vertex arrays, etc. And it's very expensive, but like in real use cases, deletions are not that frequent. So next, we're going to talk about the performance analysis breakdown of CSR++ compared to other systems. I'm going to give the performance analysis configuration first. So the graphs that we used are LiveJournal, Twitter. So LiveJournal has 68 million edges. Twitter has 1.4 billion edges. For the algorithms, we used PageRank, weakly connected components, breadth first search, and then weighted PageRank. And then for the evaluated data structures, we used CSR implementation in Greenwall. We used the adjacency list implementation from the Boost Graph library. And then we used Llama, the open source code of Llama. For the machine, we used a 2-socket 36-core machine that has 384 gigabytes of RAM. So first, we're going to start with read-only workload. This is the example of the two PageRank algorithms that we perform on Twitter and the LiveJournal graphs. So as we see here, CSR++ is very close to the fastest read-only data structure, which is CSR. It is also close enough to Llama with only a 15% overhead slowdown compared to CSR. This shows that CSR++ is very well scalable, data structures, and it scales well with the number of threads as well as the size of the graphs. So next, we're going to talk about the in-place updates. So the in-place updates meaning perform edge insertions or vertex insertions. In this example, we give some numbers on the edge insertion performance of CSR++. We show that even with a single threaded update operation, we reach up to 1 order of magnitude faster than CSR update performance. Here we have a 363 seconds compared to 40 seconds with CSR++. So in this slide, we talk about the in-place update performance of CSR++ versus Llama. What we did is that we applied 1,000 batches of new insertions of new edges on CSR++ and Llama. And then as we see here in this figure, we have Llama, that memory usage that explodes after applying around 380 batches. But whereas CSR++ continues to run the in-place updates, and while consuming almost a stable memory footprint along the way. So this increase in memory causes the system to run out of memory. So next we're going to talk about the memory consumption, which is a very big challenge when designing the data structures. So we evaluated CSR++ against CSR and then Llama, and then we found out that CSR++ has a moderate memory overhead of 33% compared to CSR. Both for small graphs and the large graphs, and then it scales well after updating the data structures. So what we did here is basically test CSR++ and Llama in both contexts. When the first context is where we don't update the graph, meaning like we only read the graph, and then we found out that this is like a 33% average overhead compared to CSR here. And then we actually tested the other case where after applying mutations. So as we mentioned before, CSR in CSR++ design is that we have to allocate double the size of the original edge arrays whenever we have to add new edges, whenever we don't have enough space, so that we have that extra space for new incoming edges. That's what's causing this memory overhead. Whereas in Llama, we actually have to create new snapshots every time we have to add new edges. So as a conclusion, we showed that CSR++ is a new scalable concurrent graph data structure that relies on segmentation technique. We also showed that CSR++ achieves best of the both worlds from CSR design and adjacency list. It allows for close analytic performance to CSR, which is the fastest read-only data structure with only 10% overhead on average. It also allows for fast mutability, meaning like we have up to 2 times speed up compared to Llama. And then it has a low memory footprint overhead, only 33% overhead compared to CSR. So that is all. Thank you for watching.